Okay. Good morning, good morning, good morning. There we go. Let's fix that up. How are we? Oh, God. How is everyone? That's what I meant to say. Um, let's see. Only 40 people here. That's not very good, is it? Where's all your team members? You got to tell them to come to the lectures. They really help. So, yes, I'm here. Alrighty, it's 5 past. I hope you enjoyed the music and the waiting room, but we've got a few different things to cover today. A bit of talking, a bit of code writing, and I think it'll take about an hour 40, an hour 45 all up. So there's some time for questions and some chit chat at the end, but it's better to get into it and then we can discuss at the end. Hello, Sasha from 1511, who's maybe in the stream somewhere. So we're all graced with Sasha's presence today. Yeah, midterm cramming for other subjects. Yeah, that's what's happening. But, well, I'm glad to have all 43 of you here and anyone else who's going to be trickling in the next few minutes. So today we're talking about a topic, basically one topic. It's I don't know if you'd call it a non-technical topic in the term, so that this isn't something that you're going to need to implement in iteration 2, for example, but it's something that you need to start thinking about because you'll be using it every day you write code for the rest of your career. So what that is writing good software. 1511, you learn how to write software for maybe the first time ever. In other courses, you learn different concepts and different ideas and different languages. And what we're talking about today is how to, no matter what you're doing, how do we make sure that we're writing good software that will last a long time? It will outlive you. That's what we want. And it's not going to crumble when something changes or a framework updates. And we're not going to get there today. This is a lifelong thing. This is something I'm still learning and something I'm still honing every time I write code. But we're going to talk about the real fundamental basic principles of what we think goes into writing good code, specifically with Python, sure, but a lot of these concepts apply to anything. So why do we do it? Why do we care? Well, it makes you happy and it makes your team happy because when you write good code, it means it works. You don't have to think about it again. The best code in a project is in the file that you never open because there's never an issue there. Maybe you need to extend it, sure. But it's the files that just work. That's good software. And we're going to talk about what makes good software, the elements of good design, and the elements of clean code. So we've spoken earlier in lectures about testing. So when we write code, how do we make sure that that's verifiable, good code, it does what we want, the edge cases mean it, etc., etc. We're not talking about testing today. What we're talking about today is design and development. How do we go about by solving a problem in a good, clean, well-engineered, well-structured way? As a quick little anecdote, I saw this come into play the most when I was working at the previous institute I was at. So we had 2 software teams, the software engineering department and the data science department. But the data science department would often write code. I mean, it's all code at the end of the day. That's why I think software engineering is the most important thing you can learn, because no matter if you want to go into data science or cloud or networking or security, at the end of the day, we're dealing with software, and writing good software is what's important. But anyway, so the data science team would write lots of code. They would build models and do whatever they're doing. And then what we found was happening really sort of time after time was that after about a year, the data science code was falling apart. And we tried to understand why that was happening. And really what it came down to is that they weren't trained software engineers. Now, that's not to slight data scientists. They were doing something different. They're trained to do something different, and that's fine. But what is the difference between the code that a data scientist wrote and the code that when we gave it to the engineering team and they would fix it up? What were the sort of things that they were doing that made that code more robust? And that's what we're going to be talking about today. So before you write any code, and I hope that, and I know that in 1511, this gets talked about a little bit. But before you write any code, the best way to get started is really a pen and paper. And it's to start thinking about the design of what you need to work on and really understanding the problem. I think this is tip number one for writing good code. What is the problem that you're trying to solve? Many solutions are written to problems that aren't understood or don't actually exist. So people misinterpret a problem and solve it in some way that never actually needed to happen. That's not good code, because it's code that didn't need to exist. But when you do need to solve a problem, once you have understood the problem, going through and planning out what is the minimum number of correct steps that this solution should contain to solve this problem. And that's really what the design aspect comes about. So it's about writing reusable and modular code. It's about writing maintainable code. And it's writing code that's robust to changes. And when we see code that doesn't do these things, we have this sort of term called design smells that we use. And you'll start to pick up on these already. And as you get more experienced, you'll smell more and more of these design smells. But basically, it's you see little things and you think, oh, I don't think that's right. And you might not know exactly why it's not right, but you'll see them and you'll think, that's not quite right. And the more you learn of these things, the more you pick them up, the better engineer you're going to be, because you're not going to write them, hopefully. And because of the nature of how software is written at the moment, where it's very agile, we're not using typical waterfall models, where a lot of time is spent on design and evaluation, it's really important that you as engineers are doing these things, because no one's going to really be telling you to do them most of the time. So there's some stats here. $500 billion per year worldwide is the cost of poor software quality. What does that mean? This comes from the idea of technical debt. Has anyone heard of this term, technical debt? People talk about it. People talk about it a lot, and it really can make or break a software company. In fact, it can make or break a lot of companies. Technical debt is where this all comes into fruition in the business sense. So the idea of technical debt is there's some problem that needs to be solved, some solution gets written, and it gets hacked together. We're not using the good software principles that we're going to be talking about. And, it might start really small and you say, look, we're just going to get this out this week. We'll fix it up next week. And of course, next week, you're putting some other fire out, so you don't fix it up, but it gets expanded. Then it gets expanded again. And before you know it, you've got this huge code base that's unwieldy. And now, a year later, someone goes to extend the code or work on it, and it's impossible. The code's a mess. It's spaghetti code. You don't know what's doing what. You don't even know. I mean, I've come across this many times. I'm debugging some code, and I don't even think that half the code that's written is actually ever called or run. This happened to someone I knew. He went out and got a job in industry. He was working, I won't say the name of the company actually, but you've all been to this store is what I'll say. And he's working on the software team, and it was his first job, and he got tasked with fixing this code base to do something, whatever. And he spent, I think, 2 weeks poring over, putting debug statements, right line, anyway, long story short, in 2 weeks, he realized none of the code was even being called. And the whole file was just ready to go. But that time, that debt, what you're really doing when you write bad code is taking a loan on your future self or the business. What does that mean? That's why it's called technical debt. Well, every line of bad code someone writes, in the future, if the code's important, someone will need to repay that debt and fix it. And this is what we're talking about. This is what's costing $500 billion per year. It's not Apple. It wasn't Apple. They're pretty good. They write good code. So before coding and during coding are the two different stages where you can work on your design of your programs. And what I really like to do if I'm solving a serious problem is to get a pen and paper out and really draw out the problem. So hand execute it or map out or draw an API model or something like that. So thoughtful planning. How do you design good code before you get to code writing. So pseudocode's a good one. So you don't want to get bogged down in the syntax of what language you're writing and what the features of that language are. Think about the steps to solve the problem and jot them down. Flow diagrams is sort of just another way of doing that, but you can probably use some online tools like Lucidchart or something. Component diagrams and state diagrams is when we start to get a bit more sophisticated with the design tooling, and you get to a bit more of a lower level design where you map out a few more key things. We talk about those in some of the later lectures, I believe. But it's basically modeling what the solution should look like. And if you do this properly, the good thing about it is that you don't invest, hundreds of hours writing code. You might spend a couple of days creating a couple of diagrams. You go to your team and you say, hey, does this look good to anyone? Do you see any problems? And then someone else says, oh, be careful when you're doing this, blah, blah, blah. You fix it up and now you've got a better design, and you haven't spent 2 weeks or an entire sprint writing code that all needs to be thrown away. And this is where, if you add this all up, $500 billion a year totally makes sense. I buy it 100%. And then it comes to when we're actually implementing the code. And just because you've planned your software well, it doesn't mean that when you write it, you will write clean, good, well-architected code. So how can we do that? Well, then we first need to understand is why we're writing bad code in the first place. And really, this is sort of the default tendency for most programmers. And why is that? Well, when you jump into writing code, you're often going to do the first thing that comes to your mind, the most common way to solve the problem. This is why a lot of you'll probably notice when you're solving some of the labs or even the project, you're using for loops everywhere, because that's sort of the default way your brain has been trained from 1511, where it totally makes sense. But we're running Python now. You got to break those habits and start using iterators and more Pythonic ways to solve the problem cleaner in the context that we are. So it's really about fighting your default nature to do the thing that would work, and to think about the best way to actually solve it. And thinking about in the future, how might this need to be extended, and how readable is this for other people? Here we get to the first code smell, called dry, or don't repeat yourself. This is a common code smell, let's call it, that you should already be, really underway in terms of being trained to spot this and to avoid it. So what does dry mean? Don't repeat yourself. And I know, again, in 1511, this should be spoken about a lot too. But it's all about, if you see repeated code, alarm bells should ring in your head, basically. So if you see 2 really similar for loops that loop over the same thing but separately, could that be one for loop, for example? So it's about writing more generic or general code that doesn't repeat itself sometimes. Functional decomposition is another way we can solve the dry problem. And we're actually going to just jump into some hands-on demos now, which I think is going to be more valuable for everyone. So we've got some code here. I'm just going to shift to my editor here. All right, let's set this up, zoom in. Let's clear this. Now I pushed some updates to some of this code this morning. So if you've already cloned the lecture code, you might need to pull. But let's see. Oops, sorry if it's named week 2, it should be 1. Don't worry about that. Alrighty, let's do it like this actually. Is this readable? You know what I really need to get into the habit of doing is this. I think that's better. Maybe, we'll see. Okay, so here we have some code. Let's quickly run through what it's currently doing. So basically, we're looking that the number of arguments passed in to the command line is exactly 2. If it's not exactly 2, we exit. And just to recap for everyone, the first parameter or argument is always the name of the program. So 2 args is like 1 additional argument. Does that make sense? So this is just, we want to see that there is an argument provided to this program. So if I call Python, this file is called, let me save this. This file is called dry.py. If I call it just like this is going to exit straight away because that's only 1 argument. It wants a number. So if, I mean, this program works. So if I give it the number 2, it's going to calculate a series of prime numbers. No, it's not. It's doing exponents. It's doing some, what it's doing doesn't really matter. It's doing some exponents in a range, basically. But this is just to check that we have an argument. Alrighty. Then what are we doing? Then we get a number from the first argument. So this, basically this 2 gets turned into an integer and stored in the variable num. All right, so that's fine. That totally makes sense. Then we're saying if that number is exactly 2, we do some code in this block. What are we doing here? Well, basically we loop in a range from 10 to 20. We do the exponent and we print out the result. And then similarly, if the number is 3, we do the exact same thing. However, we're taking it to the power of 3, not 2, and printing out that result. And then if it's any other number, we exit. We don't want to do anything. All right. So what the code does doesn't really make sense. It's some arbitrary code. But what we're demonstrating here is that we have some dry code smells here that hopefully some of you have been picking it up if, unlike PernJ, you don't have any sinus issues. Or COVID, maybe. Anyway. So what's the biggest thing jumping out at you guys? And then I'll say the biggest thing that's jumping out at me. Yeah. Yeah, exactly right. You know, we have these 2 for loops that are almost identical, except for the number that we're taking it to the power of, the exponent. And that's used twice in the print and the number. Now, this code works. It solves the problem, but we have this duplicated code smell. And just to ask everyone, because I think it's really obvious that we shouldn't have this duplicated for loop. But why is it a problem? Is it because I don't want 22 lines of code, I want less? Yeah, maybe. But what's one of the actual motivations for reducing the duplication? Why do we actually care? There's probably many examples. There's a few answers, really. Storage. So Brendan, basically you're making the optimization argument. So you're saying it'd be more efficient if it was 1 function. But really, I don't agree with that. This is just as efficient as if it was taken out into a function, right? In fact, this could actually be more efficient because you're not storing this in a function variable on the stack. So yeah, but not really efficiency. So Ben says readability. Yes, in that less code is more readable, agreed. But I mean, this is readable. It's the same for loop. I could read it if it's twice there or once, you know, you're all capable. So yeah, readability sort of. Hamish is sort of spot on with point number 1 I wanted to make. And I know a lot of you have put answers in. Sorry, I'm not reading them all. But really, to me, the biggest thing is that if you know, Hamish comes along in 12 months and there's a bug here. We need to make this range from 5 to 20. And Hamish fixes that 5, and then goes off and quits the company. Oh, but holy damn it, Hamish didn't fix it on line 16. We've now got 2 touch points that we've got to make these fixes, which is just more opportunity to fail. This is why the code smell is so important. Did anyone go to Rob Pike's guest lecture? If you didn't, you really missed out because I mean, he's an amazing guy, and we're really lucky to have someone like that come talk to us. But what he spoke about, if you don't know Rob Pike, he wrote the Go language, the Go programming language, among many other things that he did. One of the things I heard him speak about is that, and this is a concept I've heard many times before, and it's so true. The best code is no code at all. Why? Because it's less opportunities for things to break. And so that's why we want to reduce repeated code. Less code is more. Elon Musk says this too. His goal with Tesla's autopilot is to have the system use as little amount of code lines as possible. Why are all these people screaming this? Because they've seen time and time again, the bigger the project, the more opportunities it has to fail or to not live long. Anyway, okay, you get the concepts, I think. Let's actually fix up some of this code. So basically, I think what you all said is 100% correct. What we really want to do is make this function, make this block that we have repeated a function. That's a common really thing that we want to do. And probably it's better off doing this before we have any of the main code run. So, okay, let's do this. Print, let's call it calculate powers. Can't spell. We need it to have the exponent that gets passed in. And then we have some function here. And then what we can do is basically just copy this and then, now we can't just leave it like this, right? Because in the first example it was 2, but in the second example it's 3. So we need to generalize it a little bit. So that exponent now we're passing in, so this 2 is going to change to exponent. Now we're getting an error here because result is already defined in the main scope, but that's not a problem because basically we're going to delete the 2 repeated code snippets. Okay, that's fine. It's actually complaining about spaces and things, I think. So what's this saying? Oh. This needs to be indented. Okay, so result is equal to this calculation. That's fine. And then we are printing out an F string, which is saying that, so the number from 10 to 20, right? These numbers times exponent is equal to results. This should actually probably be printed out like that. That's fine. Now, what is this complaining to me about? Inconsistent use of tabs and spaces in the indentation. Oh yeah, that's yuck. Probably because it's copied from the slides. Still, it's saying that. Ooh, I see. Okay, I think because I copied this code from the slides and it was putting tabs in and then it was trying to be clever and learn that. So if you didn't see how I fixed that, you might come into contact with this too. In Visual Studio Code, there's a preference to highlight spaces. So when I highlight these lines, I don't know how well you can see it on the stream, but see there's these dots. Each dot represents a space, but it had some tabs, which is an arrow. Anyway, it was the wrong character. So that's something that you can check. All right, so we've brought out that logic, that for loop into a function. And now, right, we have these if statements here. And basically we can just call calculate powers, and we give it, the number that we're calculating. Okay, already, this is much nicer. We have this function that's doing it once. We've reduced that for loop. If Hamish comes along in a few months and changes this 10 to a 5, it's now fixed for both cases. All right, hooray. We've already solved one of the big code smells. But we can do better. We can do more to improve some of the general code quality of this little program already. So what are some of the things that I'm seeing here that we can do? Well, number one, and no, I didn't see anyone note this. Now we're getting away from that particular code smell, but we can still improve it a little bit. Well, you know what, actually, let's focus on the code smell. There's still some repeated code here. Not much. We're just calling the function, but you can see, like, if I highlight this line, it's exactly the same as line 20. That should raise some code smell warning bells again. Now, the if statement is still necessary, Justin, because we don't want to calculate it for any number. We only want to calculate it for 2 or 3. So we still need these if statements. But, well, we sort of need the if statements. There's probably a better way we can solve this. So we only want to calculate the power if num is 2 or 3. So what's another Pythonic way we can solve this problem? Well, we can say if the number is in a list containing the integers 2 or 3, okay, then we calculate the powers with num. This is a really good Pythonic optimization or readability improvement. Why is this so nice? Because now if I come along in a few months and say, oh, I want this to be 4 as well, look how easy that was for me to add. I don't have to really test anything. It's obvious what it's doing, and it's only going to run it for 2 and 3. We can actually make a really small but arguable improvement by turning this into a tuple, because now we take less memory for the declaration, because we don't actually want a list. We're not going to do anything with the list. We just want a collection containing the numbers 2 and 3. So this is a small improvement by turning this into a tuple. And otherwise now, I mean, I think this is about as good that I may, I don't think there's really any ways that you could better write that. That's a really nice scalable way. And this is where the little things, they really stack up. So if we look at the previous example, okay, if in this example we want to write, if in this example we want to support 4, I've got to add another 2 lines, and now it's 6 lines, and then it would be 8 lines, and then, it's just going up and up and up. Now in this example, if I want to add 10 numbers, it's still 1 line. It's so beautiful. It's really nice. And this is why Python's quite nice. All right, so that's a really nice improvement there. I think we've pretty much solved the dry code smell. I'm not seeing anything else here that we can reduce any duplication of, but we can still improve some of this code a bit. If anyone wants to yell out something that they've seen that they think they can improve, we can discuss and implement it. And until you guys do that, I'm going to name one small one. So this is a very no, it's not even really. No, that's fine. That's fine. Never mind. That's good. I was going to say we could use, I don't know, do we get argc in Python? No, we don't even get it. Yeah, I don't know why I knew that we don't get it. That's fine. All right, so if there's only 2, not 2, that's fine, that's good. Okay, maybe this is it, actually. Maybe adding some doc strings would probably be the next thing. We're going to talk a bit about that later on. But otherwise, and maybe maybe just adding a main guard. Maybe that's it. Maybe that's it. Cool. So do we understand? Let's just for completion's sake prove that we still get the same result. We have less lines of code. It's more readable. No repeated code, and we're really happy. Alrighty. Any questions with that? Let me run through the chat here. Yes, Stephen. Rob, it wasn't part of the John Lyons talk. This was just a few weeks ago. I made a Web CMS announcement for it, but it was recorded. So if you remind me after the lecture, I can send you the link. Okay. Alrighty, here we have sort of a bit of a teaser for tomorrow's topic, JSON Web Tokens. So you absolutely don't need to understand JSON Web Tokens at all right now. But let's take a look at these 3 lines, right? You might think 3 lines, like how could we improve that? Like there's not really any duplicated code. So, you know, what can we, what can we do here to really improve it? Well, let's look at what's happening. On line 4, we're printing a decoded JSON Web Token. So basically all we need to consider is that you have some decoded information. You can encode it as a JWT and decode it back to that raw information. On line 3, we encode the content into an encoded JWT. On line 4, we then print it out and check that it was decoded. Well, what's happening on line 3, 4? There's no repeated code, but there's some repeated constants. Exactly, Stephen. So apple, pineapple, orange, this key that we're using to decode and encode is repeated, right? I mean, it probably is worth just bringing this into... do I have an example here? Yes, I do. Very nice. This has already been solved. Okay, but you can see that we can take this key and turn it into a secret and use that in place so that if we change this, we don't have to change it in 2 places. The same concept as before. We can do the exact same thing with the algorithm, right? This HS256 could be taken out into a constant. That's fine, we could do that. What else? Probably not too much else. But yeah, so you'll come across this all the time. Keep an eye out for it. Reduce duplication as much as you can. All right, let's move to our second code smell, or called KISS, or Keep It Simple Stupid. This is what we were talking about. This is what Rob was talking about in his guest lecture. The simplest way you can do something is the best way to do it. Okay? The simplest way you can do it is the best way to do it. Sometimes, even if it's less efficient than another solution. Most code you write won't need to be optimally efficient. It's, you know, in some places where things are really scaling, sure, but not everywhere. And in many cases, the cleanest, most obvious code you can write is the best way to do it. I gotta say, I see this, I think this might be the biggest difference between a junior, well, let's say you're a good junior developer, or a mid-career developer, and a senior developer. I think this is the biggest difference between a junior or a mid-tier developer and a senior developer. I do this too. We all do this. I'm not criticizing. We have a tendency, if we know what we're doing, and you all do, you're all going to be great software engineers. We will all have a tendency to try and show off our code, our abilities. It's because we spend many years honing our craft. We understand things really well, hopefully. And if you feel like this will never be me, this will happen to you at some point because you will get better and better. But some of us just maybe do have a bit more of a proclivity to this. But we see a solution and we think, oh, I know a trick here that's really gonna be cool. And I can do this all in one line, or I can do this really obfuscated thing or whatever. And it feels great. We get to show off and prove to our colleagues that we know what we're doing. We want to flex on them. It's that simple. But once you really know what you're doing, you'll know that that's not a good idea. And the best way to solve a problem is to write the most boring, plain code you can think of. You know, I saw this. Let's see here. Let me search off stream. You know, Reddit. Oh my God. Okay, you can't make this up. So 8 hours ago on the, so I write a lot of Angular code. I don't know how well you can read this. Angular, if you don't know, is like React. It's a web framework. It's made by Google. It's one of the top 3 or whatever. So Angular, I write a lot of Angular code. Angular uses this framework called RxJS or reactive JavaScript. You don't have to think about any of that. Here is a post 8 hours ago called Angular Keeping It Simple Stupid. And I think in the post they just go through some lessons learned and some advice for keeping it simple. Yeah, if you've ever written any RxJS, like Hamish has, you'll know I really like it. It's really cool, but it can be a bit nuts. Anyway, the top comment on this post is the lead author of this library, RxJS. And the author's saying here, this person wrote this library. Their career is based off the tools that come with RxJS, right? And what they're saying here is that not everything needs to be using RxJS. It's totally valid to not use operators if you don't need them. Instead of pumping every button click into a subject and then using filters. So these are sort of RxJS concepts. The author could just do, if it's just using a classic if statement. If it's a CSV, whatever, call this function. Now, none of this needs to actually make sense, but the spirit of what the author is saying here, I mean, they say it right here. This is just a light example, but sometimes less is more. This is what I mean. Really senior people that know what they're doing, they scream this all the time and no one listens. You don't have to... The reason this is hard is because you really need to understand something before you can take a step back and then say, I don't need to do this. There's a simpler way of doing it. But anyway, it's just a topical because I saw it this morning, and I knew we were doing this lecture today. I was like, oh, there you go. So write the simplest tools to solve a problem in the simplest ways. Less code is more. Let's get some demonstrations up here. Okay, so here we have a file, a program. What is this program doing? Really simply, we want this program to print out a random 50 character length string using A to Z, A to Z. All right. So if I call random string, I want to get something, something like for 50 characters. So we're all happy with what we're trying to do here. So let's have a look at this, maybe your first attempt at how you'd write something like this. So, we've got this result string that we're going to put the result in. Okay, no problems. We want 50 characters, so we want to loop 50 times. All right, I'm still with you. All right, well, we need to generate a random number. So we're importing the randint function. I don't know what the hell that is. Let's get rid of that. We're importing the randint function from the random library. Alrighty, no problems. And randint lets you give it a minimum and a maximum. So we're generating a random integer between 0 and the length of cars, which is whatever it is, like 50, whatever, it's like 40, 56, is it? I think. Something like that. So that basically, okay, if I generate a 0, that would be A. If it generated 10, it would be the 10th letter of the alphabet or whatever. We then map that integer to a character, right? So that does the mapping. And then we add that character to the result string and return it. So if I run this, I think this fails sometimes, but here we go. No, that's right. We get back this random string. That's what we wanted. Oh, I don't know if you heard that crack. Cool. So this could be, you could argue that this is like your sort of first attempt at it. It's 18 lines of code. Is there any repeated code? So do we have the dry code smell? Yeah, there's a case where this breaks. That's not the point, Julia. Sorry. Yeah. Mikey, been sitting for too long. That's why I'm standing for the lectures. Got to get moving. Got to get the blood pumping. So is there any repeated code? No, not really. So there's no problem there. But can we improve this code? Can we write less code? I think we can. So the first thing that I want to do is that we don't really have this 50 as a constant. So why don't we do that? Random string length equals 50. So let's pull that out and turn that into something like that. You could make randcar type a function. Yeah, but we're already in a function. We want to write less code. We don't want two functions now. So we've brought this out into a constant called 50. Alrighty. Now, do we even need this line? This is where a good understanding of the language you're writing can help you understand more efficient or just use the library to do the work for you. So this is another, actually I haven't sort of spoken about this, but when we say writeless code, what we're also saying is use the libraries, because the libraries are really well verified. Your code isn't, right? So we want to use the library as much as possible. And in the library, there is, in Python, there is this string dot ASCII letters. I think it comes from string. There we go. And ASCII letters is literally this array for us, but we don't have to have this ugly line printed out. And just to prove that, if we print cars here, right, and just get rid of all that for a second, it's literally what we had typed out. Okay, so we're using the library now, and let's say in 100 years, for some weird reason, we extend the alphabet, right, and now there's a new character. I don't know how to do it. Something, I don't know. ASCII letters in theory is going to support, it's going to scale. We don't need to go back and fix the code. The library will get fixed for us. All right. So, and you can already see there's a lot less code as well. All right, let's turn this back on. All right. This is a really C explicit way of solving this problem. We can use the Python library a bit more and do some more Pythonic programming so that we write less code. Now, there's no way that you necessarily need to just come up with this solution, right? But what we're demonstrating is that there's usually a better way of doing this. Alrighty. So we can use all of this ASCII letters, right? So we don't even need to really make it a constant now because we're only going to use it once. And we're going to use this choice function that comes from random. What choice does is it basically says, given an array, pick one. Okay? I mean, that's really nice. But it's only going to pick one. It's just going to pick a letter and then join it to a string. So this could print out A or B or C or D, but it's just going to do it once. And we can prove that because we print it out here. Yep, that's fine. This should just print out one random letter every time. All right, but we want to do that 50 times. So I could, for range 50, blah, 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 I could do that. Or I could just say, hey, return this for I in, I guess I need to still do, range. Yeah, range. And I don't want to put 50. I want to use our random string length here. All right. So for an iteration of I up to 50, choose a random character and join it to a base string. And there we go. One line now. And it's a fairly readable line. You might want to add a comment to this one. I could see that. So, choose a random character from the ASCII letters list and do it random string length times. That's it. So there's less code here. There's less places to go wrong. There's one more thing I would fix here. Can anyone spot it? This is maybe a bit personal, actually. I'm not too sure. And hey, Simon, by the way. Use triply quotes. I don't know what that means. I don't know. Do you mean here? Passing the length. We've passed in the length. Hamish, I mean, I don't know if you happen to snag, doc strings, Simon. I don't know if Hamish, you happen to snag the lecture code I just pushed, or if we must think the same. But so we have this I variable here that, and you probably can't see it on the screen, but VS Code is actually saying like this is unused, but we need it because there's no way. I was looking at it would be sort of nice if you could just go for in range, but you can't do that. You need to assign an index, but we don't actually want to use it. So one really small improvement just to sort of show that we don't want to use it is to use an underscore. So we're just, it's not changing anything. It's just a variable that will be assigned I, like I could print, or not I, index. I could print that out, but it just means that it just tells a future programmer or whatever that we don't care about what's in here. It's just a placeholder. And really, this is a really good demonstration of keeping the code simple, writing less code, using the library, so using ASCII letters, using the tools that we get given. You could argue that, this is good as a constant, I think, because it gives it a name, so that's fine. Give it a doc string, and this is really good, clean code, in my opinion. So Simon says, I think Ollie is a good suggestion. No need to use a global constant like that. Yeah, that's true. I mean, so that could probably be like here. Is that what you mean? Oh, no. You're saying like, yeah, okay. You could do something like, no. You could do, something like output string length. And I think, can you do this in Python? Can you give it a default value? So this is a nice, this is a slightly different functionality, but so this will all by default be 50, right? So you don't have a global constant doing it. But why this is nice is that if I want to print out one with 20 characters, I get a 20 character string and I can override. I don't know. I just realized we've probably never actually shown default parameters. It's a really nice language feature of Python and many other languages that help us, towards this goal of writing clean, scalable code. So, I know that at the moment it's always 50. I want it to be 50, but maybe I want to change it in the future. So assign it to 50 if you don't provide it. So this is saying if no parameter is given, make it 50. Otherwise, use whatever is passed in. So it's not always going to override it by 50 with 50. It'll use what's passed in unless it doesn't exist. The other thing to keep in mind is that what Simon mentioned, what a lot of you have mentioned, you've given some other suggestions. There's not one true perfect, if there was one perfect way to solve each problem, we would actually be in a lot of trouble because we'd be out of jobs. Because you could just train something to build the right code. There is no right answer. Some people are just really good at this, and maybe some people aren't. And we all have a different opinion. Why do we have different opinions? We've done different things and we've seen different problems come up, and we have different proclivities. Our experiences guide how we think about these things. And so people like, Rob Pike, that we think, well, how does someone like that learn all of these things? They just do a lot, and they think about it and they learn. And that's what you guys need to do. Do as much as you can and see what breaks. And when something breaks, try and commit to memory why it broke so you don't make that mistake. Yeah, otherwise GitHub Copilot would solve a lot of problems, but it's not going to just yet. Yep. Yeah. So if you use underscore, it actually does tell the linter that it's not an unused variable. It doesn't complain. So this is pretty good now. Alrighty. Let's have a break. 5 to 10 minute break. Then we'll keep going with some more concepts like this. Yeah, that's actually a good point. This is probably anything. No, that's okay. No, this is still complaining. So it's just underscore. Yeah, cool. All right, 5 minute break, or 5 to 10 minute break, and I'll see you all guys, and we'll keep talking. Alrighty. Welcome back. No one said that they're good to go, but it's time anyway. So, alrighty. So a few more sort of abstract-ish concepts that are a little hard to demonstrate with code. So we'll just talk about them, I think. But as always, you can go and get the lecture notes for this for when you want to, so if you want to go over these. But all right, so coupling. Coupling or minimizing coupling is the idea that we don't want to have interdependencies between software modules or components. So this could be functions, this could be files, this could be objects, whatever the module is or the component is. We don't want a high degree of coupling unless it's necessary, and sometimes it is necessary. And yeah, absolutely echoic. This is basically the idea of spaghetti code. So when you're in 1511 and even in 1531, you're told don't use global variables, don't use global variables. Why is that? It's because it makes coupling between components. So if a global variable is used in 8 different functions, you can think of it as a relationship now between if I've got this global, it's going to come up on the, no. Let me go back here. Okay, there we go. So if I've got this global here, right, and I've got these functions in my code, all of these functions refer to this global variable, right? If one of these functions manipulates the variable in a way that this function didn't expect, you could see we're causing problems, because now this function in a way is now reliant, or this function is now reliant on this function, but this function could be reliant on how it changes global in this function. And this is where this idea of spaghetti code is coming from. And it's more than just globals. This is probably one of the first ways that you're exposed to this concept. It could simply be that we have a bunch of functions. Let's see here. How do I draw this the best way? Function 1 that calls a bunch of functions passing in. Okay, now this is maybe a bad example, and you can't even see it on the screen anyway. This is probably more relevant with object-oriented programming, I think, where you're passing the same object around many, many times. But we don't really do object-oriented programming in this course, so I won't go into the details. But really, this is an example here of the globals where you just want to avoid coupling between our software components to avoid coming up with the spaghetti code problem. Another idea is this idea that we want to work with top-down thinkings, or you aren't going to need it again. So basically, the term I've actually called this by is over-engineering, and this is something I'm also really passionate about again. Over-engineering is the idea where okay, I need to write some code. I'm writing a. Okay, let me be concrete. Actually, let me give you a concrete example. So I'm writing the discussion component of the formative system. This has happened, and we're building it for the first time, right? So I'm building like a let's go here. So I'm building like a chat. Let's see, zoom out a bit. I'm building a chat application, right? We've got our bar at the bottom where you type a message, you hit send, and the message appears in the chat. That's an awful diagram, but you get the idea. So we're building this for the first time, and I come along and I think, okay, well, the first thing I need to build, right, is maybe the backend that can store messages. All right, so I build the back end and now it can store messages. And then I'm on the front end and I go, oh, but it might not always be a string. It might not always be a string that gets sent as a message, because I think in the future, we want to be able to send audio messages. So now I've got to go, okay, so I've got to, hold on. So I've got to build my backend and now I've got to support audio messages. Oh, but they could be images, so it needs to be abstract. So I need like an abstract message thing, and I need one for images, and then I need one for audio, and then it could be something like this, and then like, oh, you might be able to reply to messages. So I need to build that in as well. Okay, all right, so I gotta go and I gotta say, well, any of these messages could be replies to each other, so I need like this abstract, okay, and this is over engineering. I've spent a couple of weeks now, and what have I got to show for it? Nothing. I've built nothing. I'm just working on this back end. And then my manager yells at me because we have nothing to ship. When all I should have really done, because right now, all we needed was a really simple chat app, and I went and overthought everything, and now we have nothing. But if it was just, you post a string to the back end, and that backend stores the string, let me go, here we go, and returns the data, I would have been done in a week, right? So don't solve problems that aren't yet required to be solved. You know, maybe I never want to send audio. We might make a business change, or something changes and we never need to actually do it. Or there's some other way of doing it. We use some library for it. No one uses the chat and we get rid of the whole chat app feature entirely. And now I've put all this effort into supporting features that I never actually implement. So don't over-engineer. This, relates closely with the idea of keeping it simple. Less code is more. Every line of code you add, you really want to make sure you need to add it. So it's less code, easier to maintain, less likely to cause problems, and it gets you to actually implement things that people can use. And if it's going well, you can extend it later. Whoops, I just went twice. And with all of these things, the trick with them is that it's all about the balance. So sometimes it is really good to think, oh, you know what, maybe in the future this does need to be abstract, so let me just let it handle some multiple types and that's it. Okay? And that's it. And then I'll get it working. And then when I do come along, because I got it working and people are using it and it's going well and I want audio, I can go and fill that out and it just works a bit nicer. So you've got to be careful. These aren't hard and fast rules. That's why we call them smells. They're qualitative. You need to feel them. So you can't apply it across the board, and really, if you should be working in a team where when you're new, when you're interning, or when you're in the industry, you want to be learning these things from the experienced people around you. Pick someone that you really think knows what they're doing, and just try and become a bit more like them. And this is all helping us write clean code. And I think clean code is really the combination of all of these different practices. Being as simple as possible and following standards and understood conventions. This is a book I recommend to almost all of my students that I get talking with. It's called Clean Code, wouldn't you know it? I should have sent like an Amazon affiliate link so I could make money off everyone that decides to buy it. You don't have to buy it. Do whatever you want. You maybe find a PDF of it at the bus stop or something. But it's a really small, I think I've got it somewhere. Oh, maybe I read it on a Kindle. It's a really small, but I think it really captures and gives you some concrete examples of all the different things we're talking about. So I really, really recommend having a read of this book at some point. And again, not everything applies 100% in all cases, but it talks a lot about, when should you write comments, when should you decouple a function and decompose it, just some tips from someone who's got a lot of experience. So it's a really good book. Okay. In Python, we often talk about writing clean code in writing Pythonic code. So for example, if we go back to this example here, using iterators over, so like for in some array, rather than using a for loop, for example. This is being Pythonic. Because clean code changes depending on the language that we're writing it on. There's another link to a recommended book here. Oh, this is just a website, so you can just read it, I think, maybe. The Hitchhiker's Guide to Python. But when we say that this isn't Pythonic, or when your tutors tell you that the code you wrote in the project isn't Pythonic, what are they saying? It's that you're not using the common tools and libraries available in Python to solve certain problems in what's considered the most readable approach. So sometimes there's no best agreement. I mean, this is the thing with all the things I'm saying, there are caveats everywhere here. But you want to write Pythonic code because that's how the language is set up to produce the most readable output. Okay, another tool that we have available to us to write readable, scalable, well-engineered code, docstrings, documentation. It's really important. Any publicly or accessible function you write, whether it be a HTTP endpoint for iteration 2, or whether it be a programming API that you're writing, you want to write docstrings. Docstrings give the users of your code some detailed information on what it is intended to do and how it's intended to work. The intent and meaning behind the code. Often the code doesn't necessarily convey what was intended to do, but a docstring should. You want to include 3 things generally. A description, so what the function should be doing. Parameters, so what is string 1 and what is string 2? The type of it, because in normal Python you don't have that type information, so you can put it in the docstring. And again, it doesn't change the code we're writing. It's just a big comment, basically, in a specific format. And then what does it return? Again, that's not conveyed in the function itself. So what's the data type of the return, and what is that return value representing? So you'll see in any of the endpoints you write for iteration 2, we need there to be docstrings for this. Really, any code that other people will call, you want docstrings. Docstrings are really good. And in the editor, here we go. In the editor, when I call functions that have a docstring, you can see I get a really nice. I get it in the editor. So if I'm like in another file and I don't know what string find does, I can hover over it and I can see all of that information, right? So editors know how to read docstring because it's an agreed upon format. I've spoken a little bit about docstrings in previous lectures. They're really important, and actually you can do some pretty cool things with docstrings and header doc and stuff. There's no one's typing. Is it all just going okay, or have I like disconnected from the stream? Give me some. I need a sign of life. I get we're not writing code, so there's probably not any questions. Okay, good. Yeah, good. That's all good. That's all good. Cool. And we did talk about docstrings in an earlier lecture, Hamish. This isn't the first time. Yeah, and yeah, actually, that's a good point. There is a auto docstring. I can show it, actually. Bit of a hack. Let's see if I've got it. Yeah, I've already got it. Okay, so how do I launch it? That's what okay, yeah. So I typed the docstring, the 3 double quotes, whatever. And it says generate docstring. This pops up because I've got the extension. And you can see like it knows, okay, here you should put your summary. It's got two variables. So it gives you just the structure of it. And then you can come and you just know that it's the correct docstring function format. So I can put like, okay, this is a string, and this does this, and this does this. Now it doesn't know that it returns anything, so it didn't put the return in, but if you had a return, so like you could write the function first, like return x plus 1 as a string, let's say, whatever, some random stuff. Oops. Let's generate the docstring, and then you can see now I get the return as well, because it's smart enough to know that, oh, I'm actually returning something. So yeah, generate docstring by Niels Werner in VS Code. Nice. It's the little things that help us, right? All right. All right, that's docstrings. Really important. They help other programmers learn what you intended to do with your function. Something though I will say before I keep going with comments in general. Docstrings are a special type of comment that they're really important. They tell us how the intent behind a function or a module or a file or whatever. A note with comments. I don't know, how 1511 talks about comments. I think comments are, especially in early programmers, in industry, I used to see this all the time, but comments are wildly overused. I'm not really going to go into it. Clean Code, this book I was talking about, has an entire chapter on comments. I really, really recommend reading it. But basically, you'll see a lot of comments like calls string find. Calls string find again, checking it's false. You'll see comments like this sometimes. These are bad comments. These are really, I really don't like things like this. This is not a complex line of code. It's really clear what it's doing. It's calling a function called string find, and it's checking that it's false. I do not need to document it. We're adding noise if we comment code that doesn't need to be commented. The best code does not need comments because it self-documents, it self-comments, right? And the other reason it's actually a problem is that I write some comment here, and I come along and this changes, and I forget to change the comment. This happens all the time. This is the number one. This is probably why I'm actually so hung up about it. So when I work on formative, I'll come along and I'll be looking at a piece of code, a function or something that I didn't write and I don't know very well, and then. Yeah, Hamish, exactly, Hamish. So I'm coming across this function that I don't know really well, and I read there's some comments, and I read the comments, and the comment says something like this. It's checking that it's false. And then I look at the code, and the code's doing something different. And you get so angry. Why is that so frustrating? Because originally, yeah, it probably was doing this. Someone's come along and changed it for a perfectly valid reason, but they've not thought to change the comment. So comments are also opportunities for things to fall out of date and miscommunicate what they should be communicating. So less is more. However, sometimes we need comments we just can't simplify the code that we're writing, and we need to describe it, and they're appropriate. Yes, use them, please. Help yourself, help it, everyone. But like Hamish said, which is why I started cracking up, like, you do not need to be like, this line increments X. If you don't know that, like, X plus 1 is adding 1 to X, you've got to go back a few steps, right? And learn some of the basics of the syntax and the language. You don't want to write needless comments. But Clean Code goes through this concept in a lot more depth. I really recommend it. All right. But docstrings are good, please. Docstrings are good. But keep in mind, you've got to keep your documentation up to date as well with your code. If you get a task to update some code and to change a few things, you've got to update the comments. It's all part of it. This is why less is more. The less code we write, the less comments we need to write, the less work we need to do, the less things that can go wrong, and we make millions of dollars with our successful startup. All right. To top the lecture off, we've got 3 tools, let's call them, that you've probably seen a little bit in Python. They've probably, I'm going to assume, not all of you, they've caused you some confusion. They look kind of cool. They reduce the amount of code we need to write. You don't really get what they're doing. So if this is resonating with anyone, let me know. You don't really get what they're doing, but people that seem to know what they're talking about seem to like them. The names don't really make much sense, and you want to learn how to actually apply them. So if that resonated with anyone, I hope so. If you're already an expert on them, then that's also fine. And you'll get a little recap. All right. So for some of these, I'm going to... Oh, no internet. What? That can't be true. So let's go back a step for a second. What are things like map, reduce, and filter? So they exist in Python. That's the first thing. They come from a built-in library Python, but they exist in other languages too. They are tools from the paradigm of functional programming. Functional programming is there are functional languages, okay, like Haskell, for example, where the entire language is built around writing functional code. They have a lot of good ideas, functional programming. Some of the ideas are so good that non-purely functional languages have borrowed the idea and implemented it in the language. The 2 big ones is Python and JavaScript. JavaScript is actually a semi-functional language, and it's sort of getting more and more functional in some ways as it goes. And Python also is not a functional language, but it has these concepts that comes from the theory behind functional programming. And some of you, I don't know if you've learned or done functional programming before. I'm not the best person to talk about it. There are other lecturers in the school that are, amazing at it, but I'm a little bit familiar with it. But what's important to understand with functional programming is that I think the core concept is that all of your functions and your program is stateless. Basically, it's like you don't store things in variables yourself. You use functions to manipulate. You still have variables and use functions to manipulate them, but you're not creating local scope and local variables and things like that. Anyway, these 3 things are concepts borrowed from functional programming, and let's break them down. So the first one is called map. All right, let's go here. Okay, let me get rid of this because this is using map. And I want to show how you would maybe write it first. And then use map to solve it in a different way. All right, so basically we've got a list of names, so that part's fine. Simon, Teresa, Kaiki, Michelle. These are some current and past tutors, so shout out. What I want to do is add, so I want it to be like Simon, Teresa, Kaiki. Whatever, you get the idea. I want all the names to be manipulated in the same way. This is something that we commonly have to do. And it expands, like this could be an object or a dictionary, and I want to add a key to the dictionary, but I want to do it to every dictionary in the list. So we use map off when we have a list of something and we want to do something to it each time. But if we don't know about map, how would we solve this? Well, probably we would go, and we could still write Pythonic code. So we go for tutor in tutors. Tutor is now equal to tutor. Can I do this? Yep. So turn it uppercase. So that's fine. Plus some strings with the 4 exclamation marks. And then now, is that going to do it in place? It might. And then I want to print, let's see if it actually works here first. Then I want to print tutors like that. That's just a comment. Python map, it's called .py. No, that didn't work. Okay, because we just, we need to put it back. So what we really now need is a new tutors list. And this actually goes new tutors.append. Take the old tutor, make it uppercase, add the characters. All right, that should, and then I just want to print new tutors. All right, there we go. So we have a solution. All right, any questions about that? I mean, it should be fairly straightforward. But we've got a lot of variables now. We've got a few lines of code. And this is a really common pattern. Why is it called map? We're mapping some change, right? Making it uppercase, adding the exclamation marks, to each value in a list. That's the why it's called map. I don't know if it's a common use of the word if you're not familiar with it, actually. I'm trying to think, but you're mapping, I'll just say it again to let it sort of sit. You're mapping a change to each thing in the list. This is such a common pattern that we borrowed the map function from functional programming to solve this for us in a better way. So how can we actually use it? All right, so here we have the same sort of solution. We have the same tutors list, that's fine. We're calling it angry tutors, I like that. Angry tutors, let me actually write it how I would write it if I was doing it myself. So we have this, I like angry tutors. We have this angry tutors, which is going to be what we get when we map some change to each name. So we call map. Now map takes two parameters. First, it takes a function. The function is the thing that will be applied to the list. Now, we could make a function. Add anger, let's call it, which just returns. Actually, let's give it the name. And it returns name.toUpper. Oh, it's right there. Yeah, sorry. Thank you, Echoic. Okay, I was just building this this function. All right. So we could give it shout. So we give it the function shout. We're not calling shout. We're not calling shout. We give it the function. The function is a variable. And then we give it the list that we want to apply, the functor. I think it's called a functor, F-U-N-C-T-O-R, that we want to apply the function to. So this is a perfectly sane use of map. If we print, now one of the issues is that a map doesn't actually produce the same type that was given. So it doesn't actually produce a list, it produces some map object. So because if I print angry tutors here, let's make this a little bigger, and I run it, you see I've actually got this map object. I don't actually have a list. But really simply, we just convert it to a list by using the list function. And there we go. I get Simon, Teresa, Kaiki, Michelle. It's yelled it. I didn't have to even use a for loop. It's less lines of code, it's functional, and it's working quite nicely. Now, maybe, like this shout function, I don't really need it to be a function. Like it's never called anywhere else. So I don't really want it to be a function. Well, what I can do is use what's called a lambda. So a lambda is another idea from functional programming, but basically it's an in-place ad hoc declaration of a function. So it's converting this entire declaration of a function to a localized ad hoc function. So to write it, we just use the keyword lambda. So we're saying I'm declaring a lambda. My lambda is going to be named t. And what does my lambda do? My lambda, now, no, that's not true. I'm making a lambda. T is the value passed in from the map for each tutor in the tutor list. So let's run through this. Map comes along and it goes for each value in the array and passes one by one the individual value to the lambda. This T represents the individual values that will be passed in. So Simon, then Teresa, then Kaiki, then Michelle. So really what I would prefer would be to call this the name. Okay? And then what follows is what we want that lambda to do. It's just a function. So we go name.upper plus, 4 exclamation marks. Let me make this a bit smaller. So what we've done is we actually declared a local function. Well, that's a problematic term because local functions are a bit different. We declared a function that only exists in this map call. And we applied it to each tutor in tutors. And that means we don't need to declare the function. If I run this, we get the exact same output. And now, well, you can see like just how little code we need to write. I mean, this is just a print here, and this is just the main guard. We're doing it in 2 lines, basically. And this line is just the data that could just be passed in. We're really doing the core logic of it in 1 line. Now, so someone asked, what does map return? It returns a map object. The reason for it is because map can be applied to anything that's iterable. So for example, this doesn't have to be an array. It could be a tuple. And if, so now what would map return? Like, does it always return a list? Does it return the thing that it was given? Now it needs to know the thing that was given. Okay, so blah, blah, it just always returns a sort of generic map object that you can turn into a list, or you could just turn it into a tuple. You can turn it into whatever you need it to be. And now we get the same output. So that's what map is. It iterates over something that's iterable, like a list or a tuple, applying either a function to it or a lambda, which is just a function that was declared inline. Whew. How's that sitting with everyone? Where's my water? Hopefully, what I want you is just to appreciate the power of it and start to think, if you ever have a list of something that you're applying everything to, maybe you can use a map to solve this. Can you pass multiple variables to the lambda? Yeah, I think you can. I think you just do this. Good question, though. But I mean, this actually, no. Ugh, Jake. You can't do this. You can't have multiple. Well, you can, but you've got to remember, so the map function iterates through each value in the list, or whatever it is, and passes the element to the lambda. So there will always only be one that's passed. You can make a lambda with multiple parameters, no problem. But for a map specifically, the map function will only ever pass one at a time. So it will never be used in a map. A lambda can have multiple parameters declared just because a function can have multiple parameters. But map will only pick one at a time. So you will, in a map, you will never have multiple, you should never have multiple lambda arguments or parameters declared. Does that make sense? Lambda is going through and it's picking Simon, then Teresa, then Kaiki, and passing it in. So it's one parameter. Can you explain what a lambda represents again? A lambda is just a function, like the shout one, returns something. It's just taking the components of a function that don't need to be declared and callable anywhere else. What have I done here? Yeah. So what is a function? It's a name. Well, we don't care about the name because we're never calling it again. So we just have this generic lambda. It's a parameter or a series of parameters, which we can have no problem. And then it's some action, which is the body of the function. So it's just a function. I mean, you don't need to overcomplicate it. It's an inline function that doesn't need to be called. It can't be called. I can't call this lambda. So another way of thinking it is it's taking a function and assigning it a variable. So I could do something like, I think you can do this in Python at least. Shout is a variable assigned this lambda. So it's turning a function into a variable. And then I can just use shout here. And again, no need to necessarily make it global. So it's turning a function into data. That's the best way to think about it. And just to prove that this, never mind. It's the two-hand job. Python map.py. And we get the same result that we expected. It's really cool. And it is really cool because now we can pass, let's say we've got a function. Whoops. Def. I always forget def. My function takes a functor. I'm pretty sure that's the right term. I hope it's not. I hope it is. And it, and I can print that out. I can pass this shout lambda around its data. What's going on here? Oh, something's broken. Oh, it's tried to import PyTorch. I've seen this happen in some of your guys' code as well. Where you hit the wrong key and it imports something crazy. Shout has become a variable. What's the variable? It's a function. I can call it. And we're going way sort of out of scope here, but it is cool. Oh, let's print that. Isn't that cool? I applied the functor. What is functor? It's a function that turns a name and a string into uppercase and adds exclamation marks. I call it on Jake, and it prints out Jake. So that's what a lambda is. Lambdas are core for all of these map, reduce, and filters because it's another concept from functional programming. Okay, we've spent enough time on map. But now that we've understood map, it's going to be even easier to understand the other ones. So let's look at filter. All right, so here's another common pattern scenario thing that you're going to come across when you're programming. I guess you don't need to import filter. All right, you've got a list. In this case, we've got a list of marks. And any failing mark, I don't want to do anything to it. right? So I want to remove the failing marks, or I want to ignore them. Okay. Again, I could make a new list, iterating over each mark, removing less than 50, blah, 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 blah. You get the idea. I'm doing the same thing over and over. I'm iterating and doing something, blah, blah. Okay, we can do better. So we have something called filter. A filter, it's in the name, takes a list and a lambda and a function, just like map, right? Takes a function. Now, a lambda's function has to be something that can return true or false. Filters lambda must return true or false. And the true or false represents if the mark should, let me try that again. The true or false represents if the filter should keep that element post filter. Does that make sense? So in this example, the lambda takes a value and a mark. So filter plucks out a mark, 65, and looks, okay, is 65 greater than or equal to 50? Yes, it is, true, so we keep it. But is 40, then it'll do 72, then it'll do 81, then it'll do 40. 40 is not greater than or equal to 50, it won't be included. So if we run just this code and then we print it out, never mind. Look at that. 40 is gone because 40 is less than 50. I didn't have to write a for loop. I didn't have to iterate. I didn't have to do much. It's such a common pattern to filter down an iterable thing like a list that the filter function does it for us. Really powerful. And this is a simple predicate, but you can imagine that this could be quite complex and it just happens really nicely for us. And all the same things we've been talking about with the lambdas applies here. It could be a function, it could just be the lambda, whatever. Cool? Any questions on filter? I'm going to assume no. And then we have reduce. That's probably the killer. Well, it's not a killer. It's probably just the most difficult to understand. But it's also probably the least used. Maybe. I mean, maybe I use it the least, let's say that. Because the circumstance that you need to use it isn't as common, but it's really powerful when you do need to use it. So reduce, what's reduce? Reduce uses a reducer function, which again is just another lambda, that takes a pair of values in a list or an iteration, something that's iterable, and slowly reduces it down to a single value. All right, so what the hell is this saying? Let's get the reduce example up. So same example, we have the marks here. So marks is an array, 65, 72, 81, 40, 56. What reduce does, let me get my whiteboard up. All right. What reduce does is given a list, this is probably the most basic example of reduce. Given a list, it takes two elements at a time. So for example, 1 and 2, and does something to the two elements. So let's do sum. Let's make a sum filter. So what do we do to elements 1 and 2? We add them together. So this could be A, we give it a variable name, and then the thing could be A plus B. So what it filter does is it goes through and it says, oh, well, a plus b is, in this case, 3. So it makes a new list, or it doesn't make a new list, sorry. It just edits the list to be 3, 3, 4, 5. Do you understand that? It took the 1 and 2, it added them together and replaced the 2 elements with the result. And then it does it again. And we get 6, 4, 5. Because it added this 3 and this 3. And then it kept the 4, 5. And then it does it again. It's every time it's reducing it. It's like when you're boiling a reduction on the stove, if any of you are really into cooking. The longer you do it, right, the less you're getting, but it's more concentrated based on the reducer. Then it's going to be 10, 5, and then it's going to be 15. And then it takes it out of the list, I think. So, and if you sum up these values, is that right? Did I miscount? Oh no, that's right. Yeah, 15. Yeah. And it gets to 15. Now, this is just sum. You would never write this. Because in Python you would just do sum of the list. But this is just how reducers work. So let's look at a more complex example. So here we have our marks again, and we have a call to reduce with the lambda. The lambda, let's look at it. And this is where reducers are just so cool, because we can do more complex logic. So here we have the 2 values or the 2 arguments. Remember, reduce, in this case, the lambda needs to have 2 because reduce picks 2 at a time. So A and B is what represents the first and the second. So this could also be like mark A and mark B or whatever. It adds them together, but only if the mark A is greater than 50, greater than or equal to 50. So I think, to be upfront, the way I sort of described this isn't exactly 100% right, because it shifts the 2 that it picks like this. But the core idea is exactly the same. So it won't apply the same reduction to the same value every time. It goes through and does it, and then does it again and does it again to slowly reduce it. So, but basically you can think of it, it's still iterating over the element. So only if the value is greater than or equal to 50 do we sum it. So this function is basically doing like sum passing marks, right? If the value is not greater than 50, we just return the second value and we continue on. And then we give it the marks list. And then we're calculating the average at the moment, but we can just print total. So let's print run reduce, and we get 314. So if we add up 65, 72, 81, and 56, we should get 314. Our reducer ignored the failing mark. Okay, and you can see that if we wrote a for loop to do this, we're just going to have a lot of, it's going to be for mark in marks. If mark is greater than or equal to 50, we're going to need a new, so passing marks is equal to a list. Passing, you get the idea, right? You append it. And then after you do that loop, we're going to need to, maybe we could then, we could use some sort of passing marks, and then calculate the average. All right. But in one line, we can apply a reducer to do it for us. So Justin, what's the difference between filter and reduce? Filter takes a single element and determines if it should remain in the list based on the lambda. Reduce has a strategy for getting a list down to a single result. Okay? Yeah, and I mean, Hamish raises a good point. We could just do something like this, you know, call sum on, I think you need to import it from maths, but for each mark in the marks, if the marks are over 50, I mean, yeah, I would argue that this is like a neater. This is a neater. This is a nice Pythonic way of solving this particular problem. But you can see that like, this is only really the case because sum is like, basically this is just, sum is such a useful reduction pattern that sum is built in, right? But if we weren't summing and we were doing something else, you can see that the reduce strategy would be beneficial. But sum is just so common that, yeah, I would prefer to see this line of code for this particular example. And then of course there's ways that you can merge all three strategies to solve, you know, particular problems. All of this code is in the lecture code repo if you want to go through it in a bit more detail. But the reason we're bringing this up is that what we want you to start doing is look for these three common patterns, you know, where you want to do something to each element in your list, where you want to determine if each element in your list should remain, or if you want to take a list and reduce it to a single value with some strategy. It could be summing it, multiplying it, some mathematical calculation. It could be calling a function that determines something based on some other random data, whatever it is. Look for these patterns and try and challenge yourself to use map, filter, reduce in these circumstances. The last topic we're going to talk about, this doesn't need too much time, is that don't be scared of using exceptions rather than trying to deal with an error case in some other way. So, you know, if you have a function that needs to take a square root of a number, don't return a negative number if it should never return a negative number. Throw an exception. That's what exceptions are there for. And we can write custom exception types. So for example, here we defined a square root exception type, and we can throw that square root exception type if we need to. So don't be afraid of using exceptions. Don't overuse exceptions. But in the case where you're writing code that shouldn't be executing or could break or something like that, don't try and skirt around it by doing something funky, because then other code that, for example, square root, might not know that it can't be a negative number. So it gets a negative number and then it keeps going and then your program falls apart. Don't be afraid to throw your hands up and say, nah, you gave me a negative number, I'm not dealing with this, here's my square root exception. That's all we wanted to get across with this slide. The last thing here, again, I've spoken about this, I mean, this is a weirder one, but in Python, you can do multi-line strings. You use a triple quote. This is how doc strings work. So you use a triple quote, and then you can have, you know, multi-lines without needing to do anything crazy. So if you go Python multi-line, you can see that this string gets printed out quite nicely. Whereas with this version, you're getting 3 plain strings printed differently. So you can do, you know, I don't know what else to say about it. You can do multi-line strings with Python. It's a really nice language feature. Not every language lets you do something like that. And with that, that is the end of the lecture. The last slide here is just the feedback slide, but and I know it's 1 o'clock and we've all got to head off, but if you just go to, actually I won't do that because then you can all see the results. But I just wanted to get the QR code up. Oh no, that's just the preview. Okay, whatever. Here's the QR code, the lecture feedback form in the comments again. But I hope you enjoyed this lecture. Something a bit different, where we're talking about patterns, strategies, code smells, ways that we can all be better programmers. If you're already on this stuff, you know, that's awesome. Always push yourself to find new code smells, build your own experience and write better code. That's what we want you to do. So have a great day, guys. I'll see you all tomorrow where we're talking about JSON Web Tokens, another fun lecture. So I hope you really enjoyed. Oops, what's happened to my stream? That's weird. I must have just done that. Yeah, I hope you all enjoyed today's lecture. I really did. I love talking about this stuff. If you have more stuff like this that you want to talk about, go to the forum and ask questions and post. You know, you don't always have to ask questions. Post stuff that you've found, and you know, I'll always happy to have a chat about it. So go off, big, excellent software engineers. Make us all proud. I'm already proud of you all anyway. Thanks everyone. Have a great day.